I've been coming to NCBS for the last few years and giving a talk on how optical tweezers work every year, so I decided not to do that this year. I decided to kind of, on the board, tell you very quickly about what the basics of optical trapping are. And I think there will be in later sessions during the workshops, you will hear more about it from Christoph. So I'll just, if you don't know about it, I'll just try to tell you enough so that you can ask good questions later and understand how it works. And so it'll be a mix of how optical tweezers work. And then I will try to get into what one does with these kind of optical tweezers, though it will not be a comprehensive review, of course, because of the shortage of time. And then I will tell you about when you learn something from optical tweezers, how can you use it later to understand cellular processes and maybe use it in some kind of a simulation or, try to understand other things. So that's the spirit with which we'll start. And Darius, I have an hour. How much time do I have? Yeah. 1 hour, right? Okay. So, yeah. So all of you know that, you know about light, and that light consists of a stream of photons, okay? And you can think of light as a stream of photons or like a wave. But for today, we will kind of concentrate on thinking about light as a stream of photons. And if we ever need waves, we will go to that, okay? But it's important to appreciate that you can think of light in both ways because of the quantum nature of light. Now, so light, as one Mr. Einstein said, consists of a stream of photons, okay? So these photons are little quanta of light. You can think of them as particles of light, which are there in the light and which move with the velocity of light. Now, for our purposes, the most important thing about photons is that they have momentum, okay? At each photon, as it is coming through, has a momentum which is well defined, the Planck's constant, in terms of the Planck's constant. But anyway, each photon has a very tiny momentum, okay? So if I hit you with a stream of such photons, but each photon has a tiny momentum, so if I hit you with a very intense stream of photons, which is coming in rapid succession, it may be possible for me to move you from here to there, right? It's just like hitting you with bullets, okay? So, and that's basically the principle on which optical tweezers work. It is that, there can be an exchange of momentum between a particle and another particle if one hits the other. That's common sense, right? So, so if I take such, if I have a bulb here which is emitting photons like this, and if I put some kind of a, maybe a fan blade here, it's not the best fan blade you will see, but if I put a fan blade here like this, it is possible to give a light which is sufficiently intense to actually rotate these fan blades. And actually there are also, satellites which are based on this principle. So satellites have kind of, large arrays on which solar radiation is incident on them in outer space. And because of that, these satellites can, go from here to there because of the momentum that the photons give to this satellite. Now, what we want to do with these photons is have some way for these photons to hold other things somewhere, okay, in a non-contact way. So it's like so what we call an optical tweezer and an optical trap here, okay. So like if I want to hold this, I have to exert some force on it and hold it somewhere or something like that. So so how do I do that? Now, intuitively, it doesn't make sense about how I can hit you with a bullet and hold you somewhere, right? Because the normal tendency would be if I hit you with a bullet that I will displace you from wherever you are. But so we have to do some little trick to change things around so that if I hit you with a stream of bullets, photons, then I will actually stabilize you in some position. And that's what an optical trap does. So how does that happen? So the way that is done usually, so some of the first things that we need to think about that the kind, so we want to trap things in space, okay? And this is normally, since we are largely a biological audience here, we are inspired by understanding biological things, that most often things happen in a watery medium, okay? So we want to shoot photons into water, and inside that water there is going to be something which we want to trap. Now, what is this something that we want to trap? These could be a wide variety of things. You could actually trap whole cells. Okay, you can take whole cells, you can trap them, maybe weakly, but you can hold them. You have a suspension of cells, and you can trap a single cell, for example. Okay, that's one way, one example. Other examples are, that inside cells there are many kinds of organelles. Okay, there are endosomes, there are mitochondria, there are many kinds of such organelles which are usually, bound by a lipid bilayer membrane. And they vary in size, of course, but a representative size of such an organelle would be 1 micron in diameter. Okay, there are things which are smaller and larger, of course, but let's take this as some kind of a ballpark size. Now, this organelle and whatever is there inside, let's say there is some material inside which is a solution of some other protein. Okay, and this membrane, which is covering this organelle, let's say a bilayer membrane, has some refractive index. Okay, so then if I put this organelle in a solution and I see it under the microscope, this entire thing has maybe a higher refractive index than its medium, which is water, and that's how I can see it. If it is the same refractive index, I won't be able to see it, okay, unless it has some color. All right. So now what happens is that if I send in a photon like this, or let's say a light beam, so I'll remove this now here. I send in a photon like this, and this whole thing, let's say, is in some kind of a chamber which is water, okay? Maybe it's inside a cell. This chamber could even be a cell, okay? So if I do this, then it is quite clear, if I keep hitting with a stream of photons, it's not a single photon, it's light, so it's a stream of photons, then this will go out like this, okay? And but that's not what we wanted. We wanted somewhere to hold this in place. And how that would help, I'll come to in a minute, okay? So what is done is that you send in this beam of light after it goes through a lens, okay? And what that does is that you can, I'll draw a representative diagram. It sends in this light beam like this. I'm drawing two representative beams at the edges, okay? We can draw things in the middle also. And this light beam goes like this goes like this. Now here, the refractive index is low. I'll call it mu L, low refractive index, and here let me call it mu H, which means it is higher than relative to this, okay? So the light will bend here, okay? Now if the light bends, it kind of goes maybe like this, something like this, and then, once it comes out, it again bends the other way, because it's now again seeing a medium of lower refractive index. So maybe something like this, okay? And exactly same thing will happen on the other side, right? And there are also, at the same time, there are things which are coming and hitting this like this and bouncing back. Photons and, and this is happening in this plane, coming out of the board and inside the board as well. So now if I look at so this is a photon coming in, going like this and going out like this. So let's say the photon or the stream of photons which come in have a momentum which is P in here, P in, okay? That's what goes in, and P out, that's what comes out, okay? What happens inside is not relevant. It is the change in momentum which is relevant here. So you can draw a vector diagram for this, okay? And I will leave that as an exercise for you. So basically you have momenta like this, and you'll have a change in momentum, delta P, right? Because of this change in momentum, that is an exercise for you, there will be an equal and opposite impulse or force on what? On this, right? And the direction of that force will be reverse of this. So in this case, it will be in this direction. Okay? And let me call this beam 1, and let me call this beam F2. And there are beams in between as well. And so therefore, so this is because of, let me call this F1. F1 is because of beam 1. Just like that, there is F2 because of beam 2. Okay? Now, each of these F1 and F2 will have components in this direction and in this direction. Okay? So this will be the component of F1 horizontal, let me call it, or whatever. This will be F2 horizontal. F1 horizontal is equal to F2 horizontal. They are in equal and opposite, so there is no horizontal component effectively. However, these F1 vertical and F2 vertical add, right? Because they are going to be in the same direction. So, okay, it's a little messy here, but F2, F1 vertical and F2 vertical are both pointing down. So there is a total force of F1 vertical plus F2 vertical downwards. Is this force somehow going to help you? What do people think? Remember that there are a lot of things which are coming here and just bouncing back. Okay? The ones which are coming in roughly in the center, and they're pushing this out. So now this you have now, by sending in the beam like this, okay, you have a situation where you now have a downward component of force which will compensate for this pushing out effect. Is that clear? If that's not clear, then I will repeat. Okay? And when that happens, when this is equal to this, and I call this F scatter, because these photons are coming and bouncing off, it's a scattering force. Okay? So when these two are equal, okay, then this thing will stabilize somewhere along this axis. Okay? So now what we have therefore done is that we have preventing these photons from shooting this out by sending them as an oblique beam. So remember, all this happened because oh sorry, I made a slight mistake here. This is kind of an oblique, it's focused, right? So it's coming in like this beam, okay? So if I just sent these beams straight, if I didn't focus it, then you would not have this component of the force. Because I did this, I sent the beams in like this, therefore I have, a downward component, and that these two cancel, and hopefully this will, this will work here now. Now, so what we have achieved by doing this is that we have trapped this object in this dimension, right? So now we are not yet done, okay? Because things diffuse away in 3 dimensions. Things don't just diffuse. If you keep it in water, it will diffuse away in all dimensions. So we now have to do something to prevent it from moving away in this plane. We have prevented it like this, and now we have to prevent it from moving in this plane, okay? Now that can be done by the same mechanism. Why? Now, so for this we have to understand, I will so now we have to understand that when we sent in this beam of light, this got focused to a tight spot, right? So we sent in, so this was, so how did this light come? So here we had some light source, okay? Usually this light source is a laser beam, okay? It is a laser beam, and the advantage of using a laser beam is that you can get highly intense light in a laser beam, and that light is very collinear, and it is at a more or less a single wavelength, etc., etc. Okay, so you can shoot in a lot of photons in a well-defined direction using a laser, okay, which you cannot do otherwise. So that's why you use a laser beam here. Now what happens is that this laser beam comes in through this lens, and it will therefore, so it's coming in like this, and it'll cross like this, right? Let's say if there was nothing there, and so there is, you can think of this part as a focus spot. There's going to be a waist like this, right? So if there is a waist like this, and in this is where I have my particle which I'm going to trap. This waist here, the rough dimension of this waist is about half the wavelength of the light that you're using, roughly, okay? So it's, and the typical wavelength, the light that you use for this kind of application is somewhere around close to a micron, okay, slightly less than a micron. So this waist dimension is between 500 nanometer and 1 micron, okay? This dimension, this waist, approximately 1 micron, let me write, is called a diffraction limited spot, okay? Because you're sending in a light beam and you cannot focus it more than the diffraction limit, okay? So it's called a diffraction limited spot, but that's a separate issue. So, but basically a spot like this, okay? Now, in this spot, you have most light here, and you have less light as you go away from the center of the spot, because you're focused clearly, okay? So, now if I were to pull this, let's say I go inside that water and hold on to this object here, and I try to pull this out like this, okay? Then what will happen is that this, let's say, and I pull it out, and let's say I'm successful, partly, okay? So the new position of this object will be maybe this, okay? Now what is happening is that there is most light at the center, and there is less light as you go away from the center. Therefore, this part of the beam, let me call it this half of the beam roughly, of the particle, will see less light than this half, right? And when that happens, the force, F2 force from this beam will be higher than the other one. Is that clear or not? Because there's less light on this side. Because the intensity of light is telling you how many photons pass per second, and each photon is giving you a little bit of kick here. But if I move it out, then obviously there's an asymmetry. Here, what happened is that it was in the middle of a potential well. You can think of it as a potential well. Okay, there's minimum energy at the bottom, and there is it's hard to stay above that. But here, if I move it out, what happens is that this part of the bead or object sees more light than that part, and therefore this component of the force increases. This component reduces. So what that does is that, I will draw this as a thick line now. What that does is that this, so in this situation when it was the center, I told you F2H is equal to F1H, right? Now that is not going to be true if I move it out. F2H is going to be greater than F1H. And when that happens, there will be a restoring force in this direction. Okay, and the same, you pull it out in any direction in this plane, the same thing will happen, because this is happening in this plane. Okay, so what that is telling you is that if I try to pull this object out here, 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 wherever, the trap will pull it back. Okay, so now what we have achieved by focusing a light beam like this is that, one, we have trapped it in this dimension. I explained to you how that happens because of this beam, okay? And also we have managed to, with the same beam, we have managed to, trap it in this dimension also. So therefore we now, if we do it right, and it needs a little bit of, you have to work a little bit on it, but you can trap something in 3 dimensions, okay? So now, what is the use of this trapping? Why would you want to do it, okay? So the first thing that it lets you do is that it lets you manipulate an object in some liquid medium. So let's say you want to engineer a chemical reaction. Okay, so let's say you have 2 liposomes, for example. Okay, lipid, 2 organelles or any 2 things enclosed in lipid, and you have reactant A in one and you have reactant B in the other one. You can use 2 optical tweezers to bring them close together, and maybe they will fuse together and something will happen. Okay, so you can engineer such reactions. You can study, so now if this particle, the other application is, let's say this is the particle. Now, obviously, if you trap something at room temperature or at some finite temperature, this object will be under constant thermal fluctuations. You put it in an optical beam like this, and there's, there are things coming and kicking it all the time, and it's going to be jiggling around, okay? Now, I will not go into how this can be proved, but I just told you that if I try to pull this out, the trap pulls it back. And this restoring force by the trap is just like a simple spring. Okay, so what I mean is that if I pull this object out by a distance x, let us say, then this, you can think of this like a spring. Okay, so it is this, you can think of this spring tied to a wall here, and this distance, let me call it x, okay, and I am pulling it out with some force. Okay, if I'm pulling it out with a force like this, the trap will pull it back, and F trap is equal to minus, why minus? Because in the reverse direction, K trap into into x, yeah, K trap into x. Okay, now suppose I am so strong, okay, I can exert one unit of force, okay, then can that force be measured here? It can be, right? Because if I know how stiff this spring is and I know how far Roop can pull this out, then this becomes this and this becomes minus K trap is the same. So I can get, right? So basically what you have to do in an optical tweezer to measure forces inside cells is that you have to see how far something can be pulled out of the center of this trap by somebody who's exerting force inside the cell. Who that somebody is, we'll come to later, okay? So that's one application. So the most important thing to appreciate about this is that it is a non-contact way of exerting force, okay? There are many other ways of exerting force. You can use AFMs, okay, for example, and each has its own advantages. But for example, if you wanted to exert a force inside the cell somewhere, you can't use an AFM, okay, because there's a membrane on top. This is one way of doing it. Another way of exerting non-contact force is magnetic force, right? You can do that with a magnet. You can do it with a magnet. That's another way of doing it, okay? And each has its own advantage. But so this is one way of exerting non-contact force. Now, what are the other uses of optical tweezers? Because this optical tweezer or optical trap, whatever you want to call it, acts like a calibrated spring. Okay, you can measure how much this. Obviously, you have to measure K trap. Otherwise, you can't measure anything, right? So how that is measured, we'll come to in a minute. But let's assume for the time being that it can be measured. Okay, if you can measure that, then you can do many things. You can find out what are the rheological properties of the medium, and how much is the viscosity of the medium in which this thing is existing. What is the elasticity of this medium in which this object is immersed? There are a lot of such things that you can do, and you can read up about it if you want to, but we'll not get into that right now. Now, so the question is, what are the caveats of doing this? So I've given you some examples where this can be done. Another example is to measure how force-generating molecules work, right? Because if this is a force-generating molecule, I can measure, I can see how it moves under the effect of the spring, okay? And I can try and understand how it works. So that we'll come to in a bit, okay? Now, the other, so you can study enzymes, and there are many such force-generating enzymes which are interesting to study and they are, for example, DNA polymerase, okay, which walks along DNA, and people have done this kind of thing with RNA polymerase. There are, many rotary motors. There are many kind of such enzymes which generate force, and you can try and study them. And okay, so that's kind of what I wanted to say to you about optical tweezers. And how much time do I have? Yeah. So is there anything that you want to ask right now? Yes.
I understood that how it is like in the XY plane, how it is restored into this place.
Right.
I also understood in the Z plane how the forces are balanced.
Right.
Now if this gets displaced in Z plane,
right.
then how it is.
If it gets displaced in Z plane, then it doesn't come back. Yeah, so you have to kind of do it right so that it goes and, it sits at a particular place in the Z-plane. You have to adjust things. You have to adjust the focusing of this beam and, so that it comes to the right place. If you pull it out, there are ways of doing this as well. It does act as like a potential well in the Z-plane as well. What many people also do is that they have two counter-propagating laser beams. That kind of thing. If you want more stiffness, more stability in this axis, people have those geometries as well. Okay. So, in a way, you have to think of this like, that it's in a 3D potential well. So even if you go in this direction, then, there is some kind of a restoring force. Though, if you go slightly away from this in normal optical traps, if you go slightly away in the Z position, it's hard to come back. Okay, and that if they'll be doing a workshop type of thing, so that when you start, if some of you are doing that, you will realize that it's when you start doing this, the first problem is that you have some spot of a laser beam and things just come and shoot out away from your focus. So then you have to play around and get it right. Okay. Okay. So this is what I wanted to say till here. Okay. Now we will. Move to one instance where these kind of optical trapping has been used really a lot to try and understand force generating molecules. Okay, and these force generating molecules can be of many types, and I will talk about the kinds that we study, which are motor proteins which work on microtubules. I'll tell you quickly what they are, but maybe I will try to digress into other things as we talk, because I don't want this to be a very focused talk on one topic. Okay, so yeah, so now there are things which generate force inside your body. There are of course many kinds of things which generate force inside your body. One kind of a molecule which generates force is something called a motor protein. And why is it called a motor? Because it moves around, simply, okay? And to move around, all of us have to generate force, okay? So this can also generate force. And so it looks a little bit like this, like, me, a smaller version of me. And it can carry something on its head, maybe one thing, maybe more things, okay? And it steps along in a coordinated manner like I do when I walk. Okay, so now when it steps, it generates a force. Now, so why does it generate a force? Why at all does it generate a force? Where does this energy come from? The energy comes from molecules of ATP, which at every step this molecule breaks down and uses the energy. Now, what do I mean by that? Is that each molecule of ATP has chemical bonds, has phosphate bonds, right? And to make the molecule of ATP, I need to put in energy into this, because otherwise you can't put charge groups together, okay? So that energy is stored, that energy comes from what you eat, is stored in the chemical bonds, in the phosphate bonds of this, okay? And this motor protein, or many other motor proteins, can break these bonds and use that energy. So it's a catalyzed reaction. It's an enzyme catalyzed reaction, and use this energy. Okay. Now the energy available from an ATP molecule is about 10 raised to the power minus 19 joules, roughly. I don't remember the exact factor, but 10 raised to the power minus 19 joules. Okay. This energy, so the energy can be written in terms of work done, right? Force into displacement, okay? So this is equal to, and you can do the quick maths, 100 piconewton into nanometer. And I'm writing this in such strange units because the forces that we will be talking about are of the range of piconewtons, and the distances that we are talking about are in the range of nanometers. That's why I'm writing it like this, okay? So this is the energy from one ATP. Okay, one ATP molecule is something like this. Okay, now, so these proteins, the kind of typical distances over which they move, as a result of using one ATP molecule, is of the order of 10 nanometers. Okay, so this distance, which comes basically you can think of it, this movement coming from one ATP molecule is about 10 nanometers. Okay? Therefore, the kind of forces, the maximum forces that they can exert will be of the order of 100 by 10, which is about 10 piconewton, right? So that's the maximum energy input, so you can't get more than that. Okay, so roughly 10 piconewton is the kind of force. It's less than this. Nothing is 100% efficient, so it's actually not roughly. That's the kind of 1 to 10 piconewton is the kind of forces that we are talking about, and you understand why this limit comes. Okay, because these things are of the dimensions of nanometers, so obviously they can't take steps which are kilometers long. Okay, so the dimensions are nanometers, and this is the energy input, so that's how much you can get. Okay, so now, so what do these motor proteins do, and what is the connection with these optical tweezers? I hope the connection with optical tweezers is by now clear, because these are things which generate force, and so this will be replaced by these kind of enzymes. Okay, and you can measure how they work, and you can understand how they work. Now, let me emphasize that what these things do, their function is directly to move from here to there. Okay, and this motion can be observed in a microscope. Maybe we'll come to that in a minute, but here is a rare instance of where you are directly able to observe somebody's function. Okay, it is not so easy in many situations. Okay, and that is one reason why many physicists and many people from outside biology are also interested in studying how these motor proteins work, because they are important, they do many things, but you can actually see things happening. Okay, so that's one reason why this is the favorite child of many people, and including myself. So okay, so now to walk like this, so this has to be this step has to be taken, then the rear leg has to go forward, and there's a cyclic mechanism, right? And this cyclic mechanism is, there is some kind of a coordination between these two heads, right? These two legs. Because when does one know that, okay, now I should release the rear leg? Okay, and then now I should step, now I should attach. So this whole thing has to be coordinated. And that's how we walk as well, okay? So now this, I want to emphasize again here that these guys actually walk. They don't swim, okay? So to walk, they need to generate a reaction against something. Like I need to generate reaction against this surface, okay? If this was slippery, I would not be able to walk. So they need to generate reaction against something, and that something is more or less rigid filaments inside cells, and those rigid filaments, if this is some kind of a cell, and those rigid filaments could be, it's a very simplified view, it's not so simple, but they could be either microtubules or more disorganized actin filaments, okay? So, and there are motors which walk on microtubules, and there are motors which walk on actin, but and they each have their own unique functions, and they do equally important things. But for the sake of today's discussion, we will not really distinguish between actin-based and microtubule-based motors. We will just think of them as force-generating enzymes, and those details we are not going to talk about today, okay? So, yes, so they move like this in steps of roughly 10 nanometer or something. Now, if I had an optical tweezer, what are the important questions to ask and understand, okay? So the important questions to ask and understand, if I was looking at a single motor, are what? Can somebody say something? What would I measure first? What? Step size comes much later. Okay, the first thing I can easily measure is how strong are these guys, right? So that's the, because I said that this is a calibrated spring, okay, and I can measure how strong this person is. So I can measure there are many things. This list is not going to be complete likely, but let's just try to. So the other thing, as Rishita said, would be the step size. Yes. What else? I'm just talking about a single motor right now, okay? We'll go to more complicated situations later. Say that again. So that's kind of the maximum force that it can exert. Okay. Yes?
Would it have something to do with the conformation of the molecule at that stage?
It would have to, yes. So, but the exact conformation of the molecule you really can't measure in an optical trap. That's something you'll have to do other things to do that. So that's important, but that's not something you'll directly really measure from this. Okay. So the other thing which of late some people, including us, have realized is that these two are fine, but for how long can you sustain this force? Okay, just being strong is not enough. Okay, how long can you sustain a force is important. Okay, and that I will try to tell you today as we go on later, and maybe in another talk that I'm giving tomorrow about why that may be important. Okay, and I will try to relate it to other things today and maybe tomorrow. So the third thing which I would like to say is tenacity. Okay, this is tenacity against somebody pulling you back. What do I mean is that, so these motors walk like this, okay, and let's say I am pulling it back, or let's say a trap is pulling it back, okay, like I explained here. So this will walk like this, but these are not covalent bonds, obviously, okay, these are temporary transient bonds, and this has a certain strength, okay, and there is a probability of this bond, there's a constant probability of this bond failing every step. Okay, so therefore, if I have motors start here and measure how far they go, okay, so one goes this far, and the second one maybe goes this far, the third one maybe it just gives up here, there will be an exponential distribution of the distances that they cover. Okay, this is like radioactive decay. This is basically telling you that there's a constant probability of them detaching every step. Okay, and therefore the distribution of this length is going to be an exponential, because there's a one rate limiting step. It's it's exponentially going to be exponentially decaying. Okay, so now even if I don't pull it back, if I let it walk, there is a constant probability that it will slip once in a while. And so typically these motors take up to a maximum of about 100 steps. Okay, this varies from motor to motor, but typically, just let's take that as a rough number, that they take about 100 steps, and within these 100 steps they may detach anywhere. Okay, sometimes they'll go a little farther, sometimes they'll go a little less. Now, however, this is the situation when you're not pulling it back. If you pull it back, then at every step they have to work against a larger barrier. It's an energy barrier. Like, so I told you that there's this potential well. Okay, if you start from here, you're climbing this well like this. Okay, and at every step there is, there's more work to be done. Okay, so there is a larger probability, and you're pulling it back constantly. Okay, and then there are thermal fluctuations and all this thing is happening, so it's not a comfortable life. Okay, so you therefore, under applied opposing load, there is a larger probability of detachment. Okay, now, and that is what I call tenacity under opposing load. Okay, so tenacity, so you can think of two kind of tenacities. One is tenacity no load, one is tenacity load. Okay, so tenacity no load is, maybe tenacity is not the right word, but you're getting what I'm trying to say. You can go so far and then it gives up. Here is where if you pull it back, it will maybe not go that far. It will give up earlier. Okay, so so these are some of the important things that you can measure. That's what comes to my mind right now. Maybe there are some other things. Okay, so that's what I can think of. And there are now, yes. Yes, people have done that as well, and I'll come to that. I will come to that. Yeah, that's a good point. Yeah, people have applied load in all kinds of directions. That this way, that way, everything people have done. Okay, so now, so how do you actually do this? Okay, how is an experiment like this done? What do you do when you want to understand this? Okay, so what people do is, I will rub this part out. That is, just stop me when you have had enough, huh? So I think I have about 15-20 minutes more. Yeah. So okay. So what were they going to say? Yeah. Yeah. So how are these experiments actually done? What do you do? Okay. So typically, as I told you, you want to, if you're doing this kind of measurements with, let's say, a motor protein or anything else, you are studying things which generate force against the trap. Okay, that may be thermal force, that may be some molecule generating force, that may be some kind of flow, whatever. Okay, and if you want to measure a force, then as I told you, you need to measure this displacement, because you have to use this equation. Okay, and you will know the K trap. Okay, so now this displacement typically is of the order of less than a micron. Okay, typical experiments is less than a micron. So that immediately tells you, if you're talking about microns, then you have to talk about microscopes. Okay, so you have to do this experiment in a microscope. Okay, so this whole thing is set up in a microscope. Okay, because you have to observe something which is very small. Okay, and in a microscope you also have something very nice which is called the objective lens. Okay, which is the thing with which you see things. Okay, and here is your objective lens, which will act, which is basically, you can use the objective lens to do what I told you here. Okay, you can focus beam. So using the same objective lens, you can see something, and using the same objective lens, you can focus light down to the tight spot which we wanted to do, and that's it, you're done. Okay, so you take a microscope. I'm not going to be able to draw a microscope here, but again, okay, I'm going to be able to draw an objective lens, I'm quite sure. Okay, so you take an objective lens like this. Normally my drawing is better on pen and paper. It's somehow very bad on boards. Anyway, so you take an objective lens like this, and you send in a laser beam. Okay, and you will see more of this in the workshop along with Darius and Christoph. Okay, now so this laser beam has to be sent into this, and the typical arrangement is that you will need a few mirrors because of space constraints. And you send in, so you will have a laser. Okay, let me just call it L here. Okay, and it sends out a beam of light, and you will need a few mirrors here and there so the point is that this beam has to go in really vertically through this objective lens. Okay, otherwise it's not going to work. Okay, it has to really go in vertically, and then you will get this kind of a situation. And you need a few things like beam expander and all that. Let me not get into that. But basically, you also need two lenses which are in a telescope, so-called telescope arrangement. Okay, so if these lenses are placed, so let's say these are identical lenses. Okay, and these both have focal length f, and you place them 2f distance apart. Then, if a parallel beam comes in, they get focused midway, and then a parallel beam goes out, right? If this is f and this is also f, that's what you will expect. Is that clear to everybody? However, if I take them closer, then this beam will slightly diverge out. If I take them farther, then this beam will slightly converge. That is useful. Why is that useful? Because if this beam is slightly divergent here, when it gets focused, so let's say when these are 2f apart, when it is a parallel beam, let's say, so this goes in through this, and now there's going to be a focus spot here. That's what I told you. Okay. Now if I make this beam slightly divergent, this focus spot instead of here is going to shift up here, because it's just going to be pushed up because the beam is divergent, right? If I make it convergent, this focus spot is going to go down. So I can adjust where in my, in the z direction do I trap this. Okay, so that's what this is for, and there are some other things which maybe we'll cover in the workshop. We'll not get into that. Why is this method better? You can move the objective as well. That is also possible. So for some, see, if you move the objective, the problem is that you want to see something at a certain place, then you will not be able to focus on the object which you want to see, which is at a certain distance away. So you want to, at the same time, focus on what you want to see, but have the trap move up or down. Because you're using the objective for two things. You're not just using it for trapping, right? Okay. So, yeah, so this is what you do in a microscope. Now, this, and here, let us say you have some object which will be in this trap, and so this laser beam comes out and it goes out, and you don't just let it go, okay? You do something more with it, okay? You put a mirror here, which is a dichroic mirror, but that's not important right now. You put a mirror here, and let's say this beam, so this beam diverges out now, okay? But you try to trap as much of it as you can, and then send it out like this, okay? And you have, okay, so I forgot that you also have another lens here on the other side of the sample. What is it? This is the objective, right? What is this lens called? The condenser lens, okay? So this is called the condenser lens, okay? Now, normally, so this light goes out, and you have another lens here, which is the condenser lens, and you reflect this out, and you send this, you have another focusing lens here, and you send this to something called a quadrant detector. Okay, so this is 1, 2, 3, 4. This detector has 4 quadrants. Each of these 4 quadrants you can think of as a detector, okay? And so this is something where if you give it so many photons, it will give you so much voltage. Simply, it's a photodetector, okay? So now, if this is an object here, the shadow of this object is going to be there somewhere on this, right? Or the shadow or image, whatever you want to call it. And if now I pull this out, this shadow is going to move in some direction. And when nobody is pulling it out, there will be 0 signal from this. Because 1, 2, 3, and it's right in the center. Right? So, I basically what I measure is the difference signal, okay? So if I have it in the center, then there will be, the difference is going to be 0 because there is equal part in all of them. But if I move it in any direction, then you will get a signal, okay? And that signal can be calibrated to measure how far this object moves. Why are we doing all this? This kind of painful. Why are we not just looking at this in the camera? How far this moves out? Yes, that's indeed true. Now, what you can also do is that you can let this slide go up ahead here, and you can have a camera here. Camera, okay? And you can measure this displacement in the camera as well. But normally, cameras are not that fast, okay? Cameras will not measure something maybe up to 100 frames per second. If you want to measure it faster, you really have to use very expensive cameras, okay?
What you detect in the photograph is not this cable, right? That's not the cable scatter?
No, you detect this. There are different geometries. You can also have a backscattered thing, but this is not backscattered. This is, just in the front geometry. So yeah, so this is the same. There's only one laser here. This is the trapping laser about what you're detecting. Okay, so the camera here. Okay, so you can also detect how far this guy moves out using the camera, but you will only sample, let's say at the most up to maybe 100, 200 times every second in a camera, okay? You can do faster than that, but it's not really practical and it's too expensive to do that. So, but here you can go up to many kilohertz, even megahertz, 1,000, 10,000, 100,000 times in a second, okay? So now, why is that important? Why is it important to measure this displacement at high temporal resolution? Is because we are talking about motor proteins or some other factors pulling this out. And let me just give you an idea of why this is necessary to do this fast, is that these motor proteins typically walk with a speed of 1 micron per second. Okay? And I told you that they take 100 steps. Okay, and each step is 10 nanometer. So therefore, they take about 100 steps in a second. So that means they take 1 step every 10 milliseconds. Okay, and these steps are probabilistic, so they are distributed in a so-called Poisson-dependent way. there's exponential difference. So some steps will happen very rapidly, one after the other, some may be slower. But there may be steps which happen therefore faster than 10 milliseconds. The average time is 10 milliseconds, but there are many steps which will happen very quickly in succession, okay? Now to detect that, you need something which is faster than milliseconds. Okay, so therefore, the rate at which you sample the position of this object, for example, in this application, has to be, in kilohertz, right? Kilohertz or more. So typically you sample at a few kilohertz. Okay, so then you are sure that you've caught everything. Okay, so so that is what basically I wanted to say. If I get into other things now, Darius, it will get late, I think. So this is a good time to stop. Yeah, so I'm going on a talk, so I'll not get into that. So this is what I wanted to tell you about optical trapping. If you have any questions, I can take that now and then we'll stop. Say that again. Right, so this size I told you was about a micron, sub-micron objects normally. You can go up to maybe okay, so that's an interesting point. The trap has an optimum stiffness. So the stiffness of the trap changes with the size of the object. So you can't trap a football in this, okay? Because your beam itself is 1 micron, and if you have something much larger, then neither can you trap something which is very small. Okay, because you just won't, because I told you this works on the principle of gradient of light. Okay, that there's more light at the center and less light as you go away. If an object which is too small, then it won't see enough of this gradient. If it is too big, then obviously the thermal forces will be very large. So the typical sizes are between 500 nanometer to 1 micron that you trap. The wavelengths of the light are 800 nanometer, 1 micron of that order. Yeah.
So you mentioned that at the ATP hydrolyzed processor step, is it possible to have an optical which hydrolyzes it, stores that, this is what the ATP stores that?
It is possible, and there are, it's obviously difficult to visualize these things. Okay, so there are, at least theoretical I know of, experimental I don't know right away, of loose coupling. So-called loose coupling between ATP hydrolysis and stepping of motors, okay? That not every hydrolyzed ATP leads to a step. So that is, those kind of things have been proposed. But largely what people think is that it is, you hydrolyze an ATP, but this has not been verified for all kind of motors. There is indirect evidence, but directly, what people have done is that they take ATPs which are fluorescent when they bind, let's say, okay? And then you can actually visualize those things happening, but that has not been done for all kinds of motors.
It's no probability that motors are working together to create strong pair forces.
Yes.
Rather than having one molecule which goes ATP and makes
Right. So yeah. So the general strategy is, as he said, to have more motors generate a larger force rather than use 10 ATPs and generate 10 times the force in a single one. Yeah. Yes. But the lower the wavelength, the nastier you get as well. So you don't want to go too low. I got a little.
Completely reflective, you can't trap.
Completely reflective, it's hard to trap. Yeah. Yeah. So like many metal particles are hard to trap. So since you. Yeah. Exactly. Sorry. You need dielectric materials. Yes. So because they'll have refractive index. Now. So there is a lot of work on trapping metallic particles as well, like gold particles he was mentioning. Now, one problem there is that most of these particles absorb radiation as well. So they heat up, okay, and that's not nice. So what I have seen in front of my eyes is that when people take out melanosomes, okay, so when pigment granules, okay, when you take pigment granules and put them in the optical trap, they will just, they'll burst, actually, because the pigment absorbs a lot of light. That's why it's dark. So, yeah.
Essentially, ensure that the particles which are trapped is transparent.
Largely transparent, but it should refract. It should bend the light. It should bend the light, but yeah, largely transparent. But even if it's Because if it absorbs a lot of the light, then you have other kinds of trouble. How important it is have this? Right. So I was actually going to talk. Yeah. So what I told you about here was that this beam that was coming in was something called a simple TEM00 mode of a laser. Okay. It's a transverse electromagnetic mode, and what that means is that the beam that is coming in has a Gaussian intensity profile. It is most intense at the center and it falls off in a Gaussian way as you go away. Now you don't have to do this, okay? You can have beams which are like this or some higher order modes. What you can also do is that you can simply put an aperture here in the path of the laser, or you can block the central part of the laser, okay? What that lets you do is that these guys who are coming and pushing this away, they get blocked, okay? And people have been able to improve the efficiency of trapping by doing this as well, but yeah, so we don't do that, but there are people who do that. Okay, thank you.
So thanks a lot. Just in time.